Right.
Hi, everybody. My name is Tyler, and we're here to talk about Machine Learning 101. I have to apologize for the technical difficulties. For some reason, my computer was not playing well with the screen. So, if you would like to have these slides on your computer, go ahead and follow along. Type in this bit.ly link to lowercase q 74, uppercase R 9, and then lowercase r. All right. My name is Tyler Stewart. I'm a software developer. I specialize in machine learning using Python, and right now I do AI for tracking satellites. Cool, right? Okay, so here is the table of contents of what we're all going to learn today. We're going to learn what machine learning really is. I know there are a lot of things flying around like, oh, AI, it's like people inside of a computer. My mom tells me all the time about how scary AI is. She doesn't really know anything about it. She just talks about like Sophia or Terminator or things like that. And after this, you guys won't do that anymore. Okay, so the how part, data preparation, data is your only friend and your worst enemy. Numerical and categorical data, data cleaning, empties, errors, and duplicates. Aggregate categories, dummy categories, splitting your data into training and test, and scaling the data along with feature selection. The how, part two, is training, scoring, evaluating the data, the root mean squared error, area under the curve, regularization, and cross-validation. Yes? I'm sorry? Go back to the beginning? Okay. All right, so. She wants to see the link again. Oh, the link. Okay. There we are. I would have been worried if I was in the middle of the thing, the whole speech, and you were like, oh, can you go back to the beginning? I didn't understand that. You want me to do that? I'll say no. All right. So, the what machine learning really is. I saw this graphic from a conference, and I thought it was really hilarious, because this is pretty much what everybody thinks of AI is. You get data, you put it into AI, and a magical unicorn comes out. So, that is not what it actually is. So we're going to do some definitions for artificial intelligence and machine learning. Artificial intelligence is getting a computer to do something that normally requires human thinking, such as driving a car. Machine learning is teaching a computer by example instead of programming explicit instructions into it. So for like a self-driving car, instead of saying turn left, turn right, we give it data. We give it video data and instructions on how to turn when it encounters certain types of video. You can't program into a car everything that it is supposed to do. It has to learn from watching videos. It's kind of like if you have a really smart child, and instead of teaching them by writing things on the board and doing math and things like that, you just give them a textbook and say, here, teach yourself. It turns out that's the best way to train a machine. Okay, so now we're going to talk about what machine learning really is. There are a couple types of machine learning. We're going to talk about supervised machine learning as opposed to unsupervised machine learning. Supervised machine learning is when you tell the computer what it's doing, you tell it what the data is. Unsupervised machine learning, I'm not going to go over because it's not super well developed, and because I don't know as much about it as I know about supervised. So, first we're going to talk about classification. So, sir, you have two bottles in front of you, and you have a plate. We can classify those things into paper recyclable and plastic recyclable. Classification is just dividing data into groups. Not very difficult. So, let's take a look at this. We have three living things. We have a cat, we have a snake, we have a person. The cat has 4 legs, it's about 2 feet long. The snake has no legs, it's 4 feet long, it's a really big snake. And the person is me. I have 2 legs, 1, 2, and I'm 6 feet tall. This is data. This is our data set. This is what we use to train the computer. So, this is a graph. Easy, right? Just 2 dimensions. Snake has 0 legs, 4 feet long. Human, me, 2 legs, 6 feet tall. Cat has 4 legs, and it's about 2 feet long. So, pretty simple stuff. This is how a computer understands the world. It puts data into graphs just like this. And then it can predict new things. Like, for instance, let's say we trained a computer on the things that are in front of you. We said, this is a paper plate. It goes in the paper recycler. These are plastic bottles. They go in the plastic recycler. Then it sees a new thing. In this example, it sees a new animal. And this animal can only be a snake or a human or a cat, because those are the only categories that we programmed into it. This blue animal, what do you think it is? Somebody take a guess. Yes? What? No, it can only be a snake or a human or a cat. So, yes, it's a cat, right? Because it's very close to, good guess though, it's very close to what the machine learning model knows is a cat. So it says, well, it's closer to being a cat than any of these other things, so I'm going to guess it's a cat. And in this case, it's right. So, a little bit more complicated example of this is image recognition or computer vision. You guys might have seen how people train computers to like put a box around an object and say this is an apple or this is a banana, right? You guys see that? Okay, this is how computers do it. Here's a picture of a cat. So each picture, like this, is made up of individual pixels. Each pixel has a color, and each color has three values: red, green, blue, right? This pixel happens to be 250 is the value of red, green is 99, and blue is 150. So what the computer does is it takes out all those letters, it says red, green, blue, just turns it into a series of three numbers: red, green, blue. It doesn't do that for just one pixel though, it does that for every pixel. All those millions of pixels in that photo, it does it for every single one. And then we tell the computer, this is what a cat looks like. Then we feed the computer thousands of images of cats, and then it picks up patterns in the numbers. And then the next time we show it an image of a cat, it might say, oh, I think that's a cat because I recognize all these patterns of numbers in it. Okay, so how many of you recognize this guy? Good, you guys are honest. How many of you recognize this woman? What? Yeah, they're real, or they're fake. Yes. If you guys want to try this out now, you can go to thispersondoesnotexist.com. You can generate your own realistic looking person. These people have never existed. They were created by an algorithm that looked at photos just like this, turned them into numbers, and then computer scientists asked it to create human faces. One of the reasons why you know these are fake is because the teeth are misaligned from the nose, and also nothing in the background makes sense. It looks like it might be leaves, but if you look closer, there's nothing noticeable. You can't really define anything in the background. Okay, we talked about classification. This is the first part, dividing stuff into groups. But what about prediction? What if some like big shot in a suit comes up to me and he says, dude, I heard you do machine learning, I'm a stockbroker, I want to know where the market's going. You use regression for that. Regression is when you want a number for an answer instead of a category. So, how does this work? Okay, I have three friends, Bob, Mindy, and Jack. Bob is super short and weighs about 100 pounds. Mindy, she's about 5 feet tall, she weighs 150. Jack is my height, and he weighs 200 pounds. So, I'm just going to grab these guys real quick. Here's Bob, 4 feet tall, 100 pounds. Mindy, 5 feet tall, 150. Jack, 6 feet tall, 200 pounds. Easy, right? Just on a graph, this is how a computer understands data. It puts it on a graph. So, I meet a new guy. His name is Mo. He's 7 feet tall. He looks very mean, so I don't want to ask him how much he weighs. So, I want to guess how much Mo weighs because I'm really curious. I'm curious how much a 7 foot tall person weighs. So, I am going to try and figure out his weight from my friend's weight. So, I just draw a line through Bob, Mindy, and Jack, and then I say, because those guys are that weight, maybe Mo is this way. And so I guess, I look at my chart over here, 7 feet, that intersects with maybe around 250. So I guess Mo is probably 250 pounds. This is regression. This is prediction. This is all there is to it. It's drawing lines through your data. Okay, so right here we have two columns. We've got your height, we've got your weight, right? These are called features because you want to use them as an input. They're like a featured movie star. They're an input to the movie, right? So this only has two features. So it's got an x-axis and a y-axis. Two columns means two dimensions. But what if we have a third column? What if we want to take into account their age as well? Then we have to do a graph in 3 dimensions. This is really hard for me to do. I've never done a graph in 3 dimensions because it's really hard. What if we have four dimensions? What if we have 4 columns? What if we have 7 columns? Believe it or not, I've worked at a company that did data science for eBay. eBay has one data set with over 1 million columns in it. So let's go back to this. What if you have 7 columns? Humans cannot think in 7 dimensions. I can't graph in 7 dimensions, and I don't think anybody in this room can. So a computer can. A computer can think in 7 dimensions, millions of dimensions, and it can create a graph of this that it can understand and that it can draw lines through. So a computer can use all this data to predict the future, just like we predicted Mo's weight. It can predict other things. It can predict other data. Okay. I call this data prep, oh lordy. And the reason why is, this is the saddest thing I've ever heard about machine learning. When I got into machine learning, I was like, yes, I'm going to make robots. I'm going to make all these cool things. I'm going to make a computer that can be my friend and all these other awesome things. But it turns out, so there's this thing called deep learning and a deep neural network. And it's been huge in the past 5 years because it can do some amazing stuff. Like you guys saw, it can create faces. It can create music because it functions like a human brain. So I thought, if I just throw tons of data into this thing, it's always going to produce something amazing. But that is not true at all, and that makes me so sad. You have to spend the majority of your time making sure that your data is clean. You got to make sure there are no errors and there are no empties. And you got to make sure that you're feeding it the right information, otherwise it won't work. So well-prepared data will make your model great, even if it's a simple program. And poorly prepared data gives you bad performance, even if it's a great program, even if it's like the best machine learning model ever. Okay, so we're starting out with our data set. This is what a data set will look like, a bunch of rows and columns. Probably not this small, you'll probably have to work with thousands and thousands of columns. So, 2 different types of data that we have, numerical, number, and categorical, putting stuff into categories. Not too difficult, right? These guys have different categories of what they eat. This guy will only eat meat. They only eat donuts, pescatarian fish, and weight is numbers, right? Okay, so we have to first remove error, or we have to remove rows with a blank or an error. Who can point out the blanks? Yes, you. Blanks. Yes, Bob and Jack for their address, those are blanks. Who can find the error? This one's a little bit trickier. Yes. No, Mo actually does live in your house, Greg. So, okay. Which one? Yes, Bob is not 132 years old. That is a typo. And the reason why that's in there is because data is often collected by humans. Data that's collected by humans can be imperfect. Like whoever was collecting this data probably didn't drink their coffee, or they were mad, they were having an argument with somebody. And so they made some imperfect data. So what we're going to do is, we found those blanks. Very good job, you guys. And you can either delete the rows with those blanks, or if there's a column that has a ton of blanks, and it doesn't really seem relevant to what you're trying to figure out, you can just delete the entire column. We are trying to figure out Mo's weight, right? His address probably does not play into that, and there's a bunch of blanks in it, so we're going to delete that. And the error, 132, he's probably 32. So we're just going to change those. Everybody understand that? Yes?
What if numerically it makes sense, but logically it doesn't make any sense? Like, takes 5 to 6 people the weight is 200 pounds, and it is restricted, which is just like a mismatch in my mind. Yeah, in each column, in each category, numerically the numbers suffice, right? But when you put everything together, it doesn't make any sense. So, what does computer do in that scenario?
Sorry, say it again?
What will computer do
That is a really good question. Okay. So the question was, what if you have, and correct me if I'm wrong if this isn't your question, what if you have a row and the data in that row does not make sense with itself? Is that what you're asking? So, like, let's say Jack was 6 feet tall, he weighed 500 pounds, his age was 2 years old, and his diet is like spare tires. If a row like that makes zero sense to you, feel free to delete it. Or there are other ways, like if you can sometimes guess if you think you know what the answer is. There's like backfilling or forward filling, but we'll get into that later. But when in doubt, just delete it. If it seems weird or wonky, you can totally delete it, especially if you have millions and millions of rows and it's not going to track too much. Yes?
So, can machine learning not detect enough inconsistency related to
It cannot.
Okay.
At least at this point. So at this point, machines cannot detect inconsistency in their data. It's like food for a machine. Like you're a human, so you can smell if your food is wonky or whatever. A machine cannot do that. It needs everything you give it. That's why so much time is put into data preparation. Okay, so aggregating categories, that just means combining categories, putting them together. If you have very few entries in a single category, or if you think two categories are basically the same, you can combine them. Like pescatarian and fish, I think it's kind of the same thing, right? People who eat fish, people who are pescatarian, pretty much the same thing. So we're going to combine those into pescatarian and fish for Jack and Bob. That's their diets. Okay, so the interesting thing about computers is they do not understand words. Even programs, when you type in words, those words are converted into numbers. They're converted into numbers that then get converted into ones and zeros. So, if we're doing machine learning, we have to convert any words into numbers. So, these are our categories, male and female, diet, meat. So, we change male and female to 0 and 1. I hope nobody gets offended at which numbers I assign to male and female. And we change the diets to 0, 1, and 2. You see, meat is assigned to number 1, donuts is assigned, or meat is assigned 0, donuts is assigned 1, and pescatarian fish is assigned 2. And we write down what those categories are. We write down, oh, gender, 0 is male, 1 is female, etc. Okay. The next part is, oh, is everybody on board? Okay, great, perfect, awesome. Next part is we split our data into two different sets, training and test. The reason why we do this is we use these guys right here to make the graph. Remember how we had the graph earlier with like Mo and the other guys? We took those data points and we made a graph, right? We use part of our data set that we're given to train this graph so that we know what to predict. And then we take another part of the data that we reserve, it's usually maybe like 25 to 30% of our data. We set it aside so that we can test our model on it, right? So that we can test and see if our graph is accurate. So that's what you do, and then, okay, let's see. Okay, so this is going to be really confusing, and I have to apologize to you for this. These numbers right here, we have to scale them. We have to make them so that they are in the same range. And the reason why is because, let's take a look at height. Those are very small numbers, 4, 5, 6. Weight, those are huge numbers. That's 100, 150, and 200. So if we have these two numbers, and we just feed them into the machine is going to say, oh, these are really big numbers. They must be super important. I'm going to focus only on this. Whereas, that might not be super important to the output. Just like age might not be super important to the output. Just because they're big, the machine's going to focus on them. And so we need to change that. We need to make it so that these are all in the same range. Like this. These numbers are all really close to 1. And because we use a scaling program, we can easily scale them back out of that. So we just hang on, and we know what we scaled them into. So we can just encode and decode them, just whatever we want. So if we get a result that looks like this, we can easily decode it back into a human-readable weight, and a human-readable height and age, etc. But we have to make sure that they're in the same area as far as numbers go, so that the machine isn't like, this is a huge number, super important. Everybody on board? Does that make sense? Okay. All right. So, feature selection. I mentioned like an actor is featured in a movie, like Tom Hanks and whoever the hot actors right now, Jennifer Lawrence. They're featured in a movie. They are the ones who determine what the box office gross is. The main actors who are featured in a movie determine how much the movie makes. So, which actors are you going to keep in that movie? Which ones are you going to kick out? So, this is our label, aka how much our box office gross is going to be. It's weight. So, which one of these actors do you think will not improve our box office gross? Which one of these features do we need to remove? So, of all these features, which do you guys think plays the least important role in somebody's weight? Pets? Pets. Good. If we look at this, I don't know, I have one cat, I don't think it plays into my weight at all. So, probably doesn't help us predict weight. We don't use that feature. We can just delete it. Congrats, now your data is sparkling clean. So, you guys might want to keep and hold on to these slides because just what I mentioned, that is every step in the data cleaning process. What's really cool, before you walked into this room, you would have no idea what data cleaning is. And now you can teach other people about it. Like people will say, oh, I got this cool machine learning algorithm. And you're like, oh, cool, well, how did you clean the data? And so you guys are experts now. Okay, so now we're getting down to business. We have a clean data set. You guys saw the data set, it wasn't clean at all. You guys cleaned it up, it looks great now. So, what we do is we want to train the model. Training a model is exactly what I showed you before, is making a graph out of the data. Sometimes in 7 dimensions, sometimes in millions of dimensions, but that is what training a model is. The model is that graph. Okay, model training, more like, this is because you don't just train it once. You have a lot of feedback back and forth that the computer does on its own to make sure that your model is the best it can possibly be. So, for instance, this is, if you guys remember, this was our prediction for Mo. We had this line going up, and we guessed, okay, I think Mo weighs 250 pounds, right? That's what we guessed. But, guess what? Mo stepped on a scale, and we saw him, and he actually only weighs 230 pounds. We were wrong. Okay, how far were we off by? Anybody? How far were we off by in our guess? Who? Yes. 20 pounds, exactly. We guessed 250 pounds. We were off by 20 pounds. That is the error. That is the error of our model. Our model was wrong by 20 pounds. Does that make sense? Okay. So, the model's guess minus the actual, what it is, the truth, that is the error. Okay. For some reason, statisticians like to make everything really, really complicated. So, the root mean squared error is you take every error, like we had 20, that was our only error because it's a really small graph, right? 20 is our error, and then you square it. So 20 squared, right? And then you add all of those errors up, because you square each and every one, and then you add all of those errors up, and then you divide it by the number of errors, and then you take the square root of that error. It's not too important right now. You can look up the formula later. It's just, you need to know that RMSE, root mean squared error, if this is really big, your model is terrible, because it means that you have a lot of errors in your model. And how you find the model, like I said, we have our testing and our training. And so Mo was actually the real thing. We tested it against him, we got an error. So if your root mean squared error is high, that means your model is bad. This is for regression when our answer needs to be a number. Okay, so now we're going to talk about how you evaluate classification. We just talked about how you evaluate regression, right? That's for predicting stocks and things like that. The root mean squared error is the main thing that you want to do. Now we're going to talk about how to evaluate classifiers. Area under the curve and confusion matrices or matrices. Okay, so we talked about classifiers. We trained a computer to figure out what a cat is, right? So unfortunately, it wasn't very good. It said that this dog over here is a cat. Obviously, it's not a cat. It said that this cat is a cat. Correct, right? And it said that this dog is not a cat, correct, but it also said the last one was not a cat. So, the machine learning model that we trained earlier is not very accurate. This is called a false positive because the machine was positive that this is a cat, but it's not. It's false, right? This is a cat. If the machine is positive that it's a cat, and that is true. This is a true negative. The machine is negative that it's a cat, and that turned out to be true. And this is a false negative. The machine says that this is not a cat, it's negative on the cat, and that turns out to be false. One way that you can look at this is the first word is reality. It's what it actually is. True or false, true or false. That's what it actually is. And then positive or negative, that's what the machine said it is. So sometimes there are contradictions. False, positive is a contradiction. Okay. This is a confusion matrix. It's a big fancy word for just putting all this stuff into a single little graph. We got true positives. We got true negatives, false positives, false negatives. It's just an easy way of organizing this. Let me just put numbers in there. So, let's do, okay, so, any questions? Do you have any questions about this? We're good. Okay. Let's do a little bit more complicated of an example of this. We're going to talk about disease testing. Okay, so I take 3,010 people and I test them for a certain disease called Awesomeson's disease. It's a terrible disease where you get progressively more awesome over time. People with stage 4 Awesomeson's disease start wearing like tie-dye and headbands, and they usually die in a hang gliding accident or from punching a shark. So it's a terrible disease. Nobody wants to have it. So we found out that of these 3,010 people that we tested, 3,000 came out true, right? Because actually we only put in 3,010 people. 3,000 of them, 3,001 of them actually had Awesomeson's disease, right? And we only had 9 people who did not. So we ran them through the test. This thing is awesome, right? Its accuracy is close to 99% because we get true positives, right? Only one person with Awesomeson's disease was misclassified because we have all these true positives and one false negative, right? So those are people who actually have it. But here's the problem. A lot of people who did not have it got misclassified as having it. Like negative, right here. Remember, negative is what the machine says, and true and false is what real life says. So the machine said 5 of them tested negative for Awesomeson's, which is great. But it said 4 of them tested positive, and that was false. So for true positives, great, we got 99%, but for false positives, we get 44%. Not good. So if you only looked at the true positives, you're like, great, this machine learning algorithm works awesome, but it does not. In fact, you could get an even higher accuracy if you made it so it classifies everybody as having the disease, which is not what you want to do. It's like if you take a test, you want to know what the truth is. You don't want to automatically say that you have a disease, right? Okay. So this might be complicated, but it isn't. So just like we talked about, true positives, good, false positives, bad. This is the curve that compares them to each other. You don't need to know how this works. All you need to know is if the curve is up here, it's great. If the curve is in the middle, it's not very good. If the curve is here, it's worthless. I like this graph, and I picked it particularly because it doesn't say good, excellent, and bad. It says worthless, which is a particularly mean thing to say, and I love it. So the reason why this is worthless is because this is 50-50. This is as good as flipping a coin. And you don't want a machine learning model that does that. This one is slightly better, this big one, slightly better than 50-50. And the yellow one is excellent. So if you have an AUC that looks like this yellow one, you're in good shape. Like I said, low RMSE, low root mean squared error, great. Your model's awesome. If it's a regression model that's predicting numbers. If it's predicting classes, then you want something like this, and you want it to be the yellow one up in the corner. So AUC, area under the curve. Those are the 2 main evaluators that you need to know if your model is working good or not. Okay. All right. Who knows what overfitting is? Who's ever heard of that phrase? Okay. when I first heard about overfitting, um, I thought it was crazy because I was like, how could a model be too good? How could your machine learning thing be too awesome? And so I learned. This is a model. She fits her chair, right? It's a good fit for her. This is a model fitting the data. This is a model underfitting the data. She does not fit that chair at all. This is a model overfitting the data. She fits the data too well. And if you freeze her in place, try to put her in another chair, she's not going to sit in that chair very well. So here's graphically that showing. This is underfitted. It's like, model, did you even look at the data? Like it's not this at all. A good fit is like this. You've got this curve is nice. You've got these points. It's not exactly right there, but it'll probably generalize really well. If you give it completely different data, it'll track that data pretty well. This one is overfitted because it was too controlling. It wanted to fit every single point in there. It was like, I have to get every single little point in here. It has to be perfect. And that's bad because if you put in another data set, it's not going to have those same little contour curves. You know, just like the flattened doll of a woman who's sitting on a bed or on that couch, she's not going to fit on another couch. So this machine learning model is not going to fit on any other data. So your goal is to find something that's a happy medium between here and here. Okay. So here are two ways to overfit your model. This is how to do it the wrong way. We talked about features, right? If you have too many actors in your movie, it might not make very much money, right? It might not be a very good movie. Second, the coefficients of the variables are too large. Like, remember when we talked about scaling down the data? That's because your machine will focus too much on the big numbers. And so if you have big numbers in front of your variables, like if your feature is a number and it gets multiplied by a number, right? Then if that number's too big, then you're going to have to end up with these wonky curves. So, like for instance, y equals mx plus b is this line thing right here, right? So, if you have your m, your slope of your x, if it's a huge number like 538, 34, and 003, that's a good sign that your graph is going to be too wonky and it's going to follow the points too exactly. Okay, so I think this is the last thing we're going to talk about before we get to the super fun stuff, which is going to show you why you're learning all this stuff, because you get to do really cool things. Okay, so picking models with cross-validation. Here's your data. It's a big old chunk right here. That's your data. So what you do with this, you divide it into multiple parts, or folds, that's what they're called. And you say these 4 parts, these are training and testing. So that should be a little bit familiar to you guys, because we talked about splitting your data set into training and testing. But we're going to do something a little bit different. It's kind of like a carousel, or like a roundhouse. What you do is, your testing set is at the end, right? Then you train it, and then you test it, and you evaluate the model. You get your root mean squared error, or you get your area under the curve, right? Like we said, that's your evaluator. You get that over there by testing it. Then, you switch which one is the testing and which one's the training. And then you keep doing that. Then you keep doing that. And you keep doing that. Until every one of these has had the chance to be the testing. Every one has been the training. Then what you do is, after you've had 5 different test sets, you will have 5 different results, right? You will have 5 different evaluators. You will have either 5 different root mean squared errors, or you will have 5 different values for area under the curve. Then you just take those and you average them, right? You just add them together, divide by the number of training folds, number of times they did it, and that's a whole lot better than just training and testing once. It's called cross-validation because it's kind of like testing 5 times using the same data instead of just training and testing once. This works for choosing what kind of algorithms you want to use, like a deep neural network, as opposed to like decision forests or whatever. And it works for choosing features. Like we said, if we have like a bunch of features, a bunch of actors, a bunch of columns, this will help us choose which ones we want because we can test it once, taking out one of the features, then we can test it again, taking out a different feature, and find out which model is most accurate with which features. Okay, so here's a more scientific approach to selecting features instead of just eyeballing them and being like, I don't like that one. So, okay. So, it's been proven that companies with more diversity make more money. As in, companies that have one type of person make less money than companies that have all kinds of ages, races, ideologies, etc. So, variance is kind of like that. Variance is not diversity of people, it's diversity of data. So, for instance, you want to take out columns that have very low variance. For instance, if you look over here, hours of driving per week stays the same. It's always 10, and everything else is changing, right? Low diversity, low variance, you don't want it. It's probably completely useless. The data changes, this column doesn't, it's probably useless. It has low variance. So they're probably not related. Okay, that's the first one. Okay. All right, so another way is only using high variance features. Like I talked about a data set with over 1 million columns. You are not going to go through that one by one and look at it and scratch your chin and say, is this column useful or not? No, I don't think so. I'm going to delete it. That'll take you years to do. So what you do instead is you tell the computer to automatically pick maybe like the 10 most powerful columns, the 10 most important columns, and incorporate those into your model. And how you do that is honestly you just tell the computer to find it. You say, I want columns that are this powerful in the model, columns that are this predictive to the output. Like for instance, height is a really, really powerful column, a really powerful predictor of weight. The taller you are, probably the more you're going to weigh. So that would probably be number one, and you would tell the computer, pick the best ones, and it would definitely pick height. So another way to do this is called dimension reduction. Remember how we said if you have 10 columns, it's in 10 dimensions? Dimension reduction is reducing the number of columns you have. And there's this thing called principal component analysis, or PCA. Don't worry about it, it's kind of a nonsense word. You can just call it PCA. And how you do that is, here's a data set in 2 directions. This one's going to be easy. So, if you can only pick 2 directions, which one do you think has the most diversity of data? Which one do you think has the most variance? Up or sideways? Perfect. Great. Sideways. That's the principal component. You guys know principal component analysis right now. Good job. The second most. Give you a hint. It's the only other remaining direction. Up and down. Perfect. Great. Principal component analysis. We just looked at a data set and we found the most important features. It's left to right and up and down. You do that by looking at the diversity of data, the range of data. Okay, so, and like I said before, you can cross-validate while removing features, and you'll see which model is the best for you because you have those accuracy measures, the RMSE and the area under the curve. Okay, so now we're on to the fun stuff. We're going to stop learning, we're going to have fun. Okay, so this is the coolest thing I've ever heard of machine learning doing. It is a machine that takes in research papers and outputs scientific discoveries that no one has ever thought of before. This machine, what it did was it was fed 5 million papers on something called like thermoelectric materials, right? And then it spat out 10 new undiscovered thermoelectric materials. Scientists are now testing those things. They've never been discovered before. No one has ever thought to make these things into thermoelectric materials until this machine came along and said, hey, let's do this. Okay, this one is really cool. Okay, I don't know if you guys heard, but there is a nonprofit called OpenAI. One of the people from it comes here sometimes. They created a text generation engine called GPT-2. They made it, and they said that it was too dangerous to release because it can create text that looks and feels like a human wrote it. So if you guys want to check this out, if you guys want to try it for yourself, go ahead and go to this link right here. It's really, really cool. I typed in, like, I just said, I love my dog or something. And it wrote out, like, all of these paragraphs about, like, the experience of babysitting my dog and what happened and all these other things. It was even numbered. It was like, I learned the following things when babysitting this dog. It said number one, he likes to go outside. All these other things. It was incredible. It was generated by a machine. It was on topic to what I had said. So, you guys want to test that out? You want to try something that OpenAI said is too dangerous to release? Check it out. And that's the end of my talk. Thank you guys so much. Any questions? Yes, sir.
When you suggested you call it, say, do you have a column of gender, like female?
No. It depends on if it's important to the data set or not. I'm trying to think of an example of when it would not be.
Because of variation of variation, right? It's either it's black or it's
That's a really good question. I would say in numerical data you want to remove variation, but if it's categorical and it's like thousands of men and only one or two women, and it doesn't really matter, then you can probably. So that's a good question. I think it depends on the situation. So, any other questions? All right. Yes, sir.
you always recommend always
Yes. Well, that's a good question. You always have to scale numerical data. Always. That's it.
That's regardless of what algorithms.
Yeah, that's the breaks. For categorical data, there is a way to scale it. It's kind of different. It's called the one-hot encoder. I didn't cover that today, but if you'd like to, we can talk about that. Okay. Any other questions? Yes. I'm sorry.
When you train your machine learning model, when you're confident that
I would say after you've been doing this for like 10 years, I don't know how. Okay, so the evaluators that we talked about, like root mean squared error and AUC, those are kind of your guiding compass. And so if they're bad, then you might need to go back to your data and clean it up more. So it's kind of they call it an iterative process. You do it, and then you go back, and then you do it again, and do it, and you go back again. So when your RNSC is low and your AUC is high, close to 1, then you know that you're clean up your data. Okay, anybody else? Yes, sir. Yeah, I mean, we could, yeah. Okay, so here's the deal. The one that I have, you guys want to see UPG2? Okay, so the one that I'm about to show you now is not the full version. So it is not as awesome and as nuanced as the full version. The full version is a little bit harder to use, and it will take me a while to get it going, but we're going to use the simple version. All right. Okay. All right. Okay. Give me something to say. What do you guys want to say? What's our customer problem? Give me something to say. Anything? That's all, folks. All right, let's see what we got. Why is that not working? There we go. That's all, folks. I hope you're having a wonderful weekend, and I hope I don't have to tell you it's been a bad few weeks, and I missed a bunch of shows and meetings as a result. I'm not going to lie to you, and I'm not going to try to. I can't imagine the state of the world without the internet. I don't mean that in a bad way. I'm saying we have an awesome resource to help people all over the world get what they desperately need when it comes to food. I know that you know this better than the average citizen. I understand the situation. I've also been asked to write a blog post on the topic, and I will write about it. I'm going into this like I have every other interview. I'm going to hit the ground running. I have a list of interviews scheduled to take place in the next few weeks. I also have a list of shows I can't make. I just want to apologize to you all for not being on the show yet, but
So this was all written by a machine. It was all created just now. The reason why this is so dangerous is because people can create fake news instantly. People don't have to spend an hour writing a fake news article. They can write Donald Trump assassinated, and they can put in and then create this article. Actually, well, no, I'm not gonna write that because I'll get put on the list. But it will create an article with details about where and when the assassination happened. And all of this cool stuff, it looks exactly like a real news article. And you could publish 10,000 of these every single day and fill up the internet with fake news. So that's why this one is so dangerous. There's another thing that I'm not going to show you guys unless you want to come up and talk to me. You can transfer image style. You can take a photo of yourself and make it look like a painting. And that was really cool. Okay, so that's the end of my talk. Thank you guys so much for coming. Really, really happy to see you here. If you have any more questions, come up and talk to me after. Thank you guys.